So conservation of a pendulum. Let's look at a pendulum. I take the pendulum and I swing it out to some starting position. Here it is swung out here. What is the initial energy state of the pendulum right there? If I take a pendulum, here it is. I swing it out to here. What's the initial state? mgy, right? Which is what? Be more generic. It's just potential energy, right? If I just pull it out and hold it there, it has just potential energy. So it has some potential energy here, which is mgy. The problem is, what is y? When we're dealing with potential and energy, we're measuring from where? So if I hold this pendulum out here, is y the distance from here to the floor? To the equilibrium. So it's really from here to whatever its lowest state is, right? Which is there, which is still a couple feet, foot and a half off the floor. So recognize that potential energy measures from wherever its minimum point is up. On the slide. Because when I get to the next thing, it's, I'm pointing out that that's the lowest point. That's not necessarily the ground, that's just the lowest point it can get. So mgy. I get to the bottom, so I let the thing go, it starts to swing, gets down to here, swings through. What do I know about the pendulum at that point? When it's at this lowest point. Does it have any potential energy left? No. It can't get any lower. It's at its lowest point, so it's lost all its potential energy. What else do I know then? If it's lost all its potential energy, then therefore it must be all kinetic energy. If it's all kinetic energy, what do I know about the velocity of that pendulum at that point? It's at its what? Highest. It's at its maximum velocity. It can't get any faster than that. Because once it swings past that equilibrium point, it's beginning to slow down as it goes back up. So what's the energy down here then? It's all kinetic energy, right? Which is 1/2 mv squared. Okay? Does it stop there? The pendulums just stop. What do? They keep on going, right? And they end up there. We're all back to potential energy. Equals mgy. Now, if I'm in physics land, what do I know about this y and this y? They're the same. Why are they the same? In the real world, will they be the same? Let's turn this on to get it. Why won't they be the same in the real world? We lose energy to other things, such as the most common one, friction. We lose some energy to friction. Friction at the point and the top, air resistance. But if I live in physics land where I have a perfectly frictionless situation, if I start from some height, the pendulum will end at the other height, exactly the same height. And it moves back and forth. If I want to find what is the velocity of the pendulum at some point, say right there, I can use conservation of energy. Energy initial equals energy final. This is my initial state. That's my final state. That would be mgy equals 1/2 mv final squared. What do I see go away? Mass. Now, this is like the 4th or 5th time now this semester. What is the thing making this pendulum go up and down? Gravity, right? And what have we been talking about from the very beginning with gravity? It accelerates everything independent of mass. Again, we see mass does not determine the speed of a pendulum because it's gravity that determines it. So if I hooked twice as heavy a weight on this thing, the pendulum would still swing at the same rate because it's mass independent. It's the length of the pendulum that actually determines the speed at which it moves. It's time. All right, so let's see if we actually trust that this pendulum will not go to a higher height. So if I take this pendulum and I stick my head against the wall and I let it go away from me and come back, my head against the wall, do we trust physics enough? We used to call this a suicide pendulum, but we can't anymore because that's not politically correct. So hold my head against the wall, bring it up to my nose. Nothing. Nothing to worry about. Now, those of you who are sitting right here, how much did I actually lose? About an inch. You actually lose about an inch. We lost an inch worth of height to friction. You don't have to worry. It cannot get higher than what it started. So I never have to worry about it hitting me. The only way it would hit me is if I did what? If I gave it a little push, right? If I pushed it away from me. Or if one of you kind of gave it a little push halfway along the way. It's not going to come back. Now, you actually, very, very few people could stand there still without your head against the wall because you do one of two things. You either actually lean forward, and then when it comes back, it does hit you because you've moved forward, or it's, natural reflection is to move your head back when it comes up at you. But you don't have to worry. Conservation of energy is not going to get higher than it started. It will not get higher than it started because if it got higher than it started, what would that mean? Gravity's going this way, or just think in terms of energy. There's added energy somewhere, right? If it started with a certain amount of energy, swings away and comes back, if it ends up higher, somehow it gained energy along the way. Something would have to put energy in. And that would be, if we had that situation, then the change in energy would equal work. We would be adding energy somehow. We're not there yet.